Hello. So in lecture number 4, we talked about systems with variable mass. We took the case of 3 problems. The first one was the falling raindrop problem. In the second one, we considered the case of a rising balloon. And in the third case, we used the case of a moving conveyor belt. Now, in all the 3 cases, the mass lost or the mass gained is typically at zero relative velocity. That means, if we consider the first problem, the falling raindrop, we saw that when the raindrop falls through the cloud, it's going to gain some kind of mass because it's gathering moisture. However, the mass that is gathered has no velocity. Similarly, in the case of the second problem of rising balloon, what happens like after an equilibrium position is reached, some amount of sand is being thrown away from the balloon, which allows it to rise further upwards. Now the sand, when it just leaves the balloon, what happens is like both of them has the same velocity. What I mean is like, so this is our balloon, they're both rising upwards with a velocity v. The moment they are released, that means the instantaneous velocity of this particular sand that is leaving the balloon is also having the same velocity as the rising balloon, because initially just before it left the balloon, it was also moving upwards with some velocity v. Same was the case with conveyor belts, but in today's problem we're going to consider the motion of a rocket. What happens is like the motion of a rocket is not going to be similar to these 3 cases. So what happens, we have a rocket, let's say a rocket that is of mass, let's say m, which is a function of time t. This rocket is moving with a velocity v, so let's note that down as well. So the velocity of this rocket is v of t, it's a vector quantity. We will calculate the momentum of this particular rocket at time t. Then we'll also measure the momentum of this rocket at time t plus delta t. That means after some time delta t has elapsed. In that case, the rocket, what happens is that a rocket actually consists of what? It consists of a fuel tank which is filled with lots of combustible fuel, and there's the combustion engine which burns this fuel, and the burning fuel exhausts the rocket, and because of this the rocket propels further forward, let's say with a velocity v plus delta v. Now let's assume that delta m amount of mass, this is the amount of fuel that is leaving the rocket or just exhausting the rocket. Now this is exhausting the rocket with a relative velocity of u. This is going to be a different velocity, and this particular velocity u is measured from the rocket's frame of reference. As the rocket moves forward with an acceleration, we are referring to a non-inertial frame of reference. We need to keep in mind that the conservation of linear momentum happens only in inertial frames of reference. So that means whenever we are determining the momentum p at time t and the momentum at p of t plus delta t, we need to make use of this velocity v vector, which has been measured in an inertial frame of reference, and not make use of u vector. And even if we use u vector, that has to be written in terms of the velocity vector v. So the momentum p of t will be the mass of the rocket plus the fuel times the velocity of the rocket v, which is measured in an inertial frame of reference, that is with respect to Earth. And for the momentum calculated at t plus delta t, so that will be equals to, so we have mass of the rocket m minus the amount that has exhausted the rocket times the velocity v vector plus delta v vector. We will also have another term here. Now that is the momentum of the fuel which has left rocket. Now since it's exhausting the rocket with a velocity of u vector, but as I mentioned, u vector is measured in terms of the rocket frame of reference. We need to measure it in terms of the inertial frame of reference. So that will be u vector minus v vector plus delta v vector. So that means the momentum of this particular mass, since it is in the opposite directions, we have negative delta m times u vector minus v vector minus delta v vector. Right, so we have the value for p of t plus delta. So let us expand the expression. M times v vector plus mass of rocket times delta v vector minus v vector times mass of the fuel minus delta m times delta v vector minus u vector times delta m plus v vector times delta m plus delta m times delta v vector. So here few terms will get cancelled out. So we have negative m delta v vector and positive m delta v vector. They cancels out. And we also have v vector delta m, negative v vector delta m cancelling out. So that leaves us with m v vector plus m delta v vector minus u vector delta m. So this is the value of p calculated at t plus delta t. So now that we have p of t and p of t plus delta d, so let's try to find out the value of the rate of change of momentum. So dp over dt, so that will be simply equals to limit with delta t time going to 0. We have p of t plus delta t, so that means m v vector plus m delta v vector minus u vector delta m minus pt, so that is mv vector whole divided by delta t. Let me quickly write it down in a much more cleaner space. So we have dp over dt. We immediately see that mv vector and mv vector, negative mv vector cancels out. So that leaves us with limit delta t approaching 0. We have delta v vector divided by delta t times m minus limit delta t approaching 0. We have delta m divided by delta t times u vector. So we have m dv vector over dt minus u vector dm over dt. So this is dp over dt, or this is the external force on the rocket. However, we have m. This m represents the mass of the fuel that's leaving the rocket. However, we need to represent it in terms of the rocket's mass. So that's quite evident that rate of change of mass dm over dt, that simply equals to negative rate of change of rocket's mass. So let's replace this, and that should give us f vector, the f external vector, that is equals to m dv vector over dt plus u vector times dm over dt. So this is our rocket's equation. Now that we have the equation of motion for the rocket, let's try to analyze some of the situations using this rocket equation. Now first we'll note down the rocket equation. So that will be the F external is equals to m, the mass of rocket, times dv over dt plus u times dm over dt. So we're considering the scalar form. Now the first scenario will be rocket moving in free space. So that means when the rocket is moving in free space, there will be no external force exerted on the rocket. So we can say that F external will be equals to 0, such that our equation now becomes m dv over dt plus u times dm over dt, that is equals to 0. Or we have m times dv over dt as equals to negative u times dm over dt. Now separating the differentials, we have dv equals to negative u times dm over m. Now we're going to integrate both sides, and for velocity we're considering the limits that it starts from v0 and the final velocity of v, and for the mass it starts with an initial value of m0 and ends up with a mass of m. So that's integrated. Integration of v will be v, and using the limits we have v minus v naught equals to negative u. So we have integration of dm over m, so that's simply natural log of m, and when we substitute for the limits we have natural log of m over m naught, or simply v minus v naught is equals to negative. If we take it inside the logarithm, so the ratio will flip, so that means we have m naught over m. So we can finally write v minus v naught as the change in velocity v, which is equals to u times natural log of m naught over m. So that means our final equation of velocity of the rocket when there is no external force present is a function of mass, which is in turn a function of time. So this is the required solution to the problem. Now we come to the second case. So here the rocket will be moving under the influence of gravity. For solving this problem, we are going to consider vertical ascent. Now, the external force F external will be equals to negative mass of the rocket times gravitational acceleration due to gravity g, and this force is going to be negative because we will consider the ground to be at the reference level, and as the rocket moves upwards with a velocity v, and this is the direction where external force will be, the gravitational force which will be in the downward direction. That's why we have the negative mg. So let's solve this. So we know that the rocket's equation is given by m times dv over dt plus u times dm over dt. So that's equals to negative mg. Since we need an equation in terms of velocity, so we'll keep the velocity differential on the left hand side. That gives us m times dv over dt equals to negative mg minus u times dm over dt. Dividing both sides by m, we have dv over dt equals to negative g minus u over m times dm over dt. Separating the differentials, we will get dv equals to negative g dt minus u times dm over m, and then we're going to integrate. So the limits of velocity will be from v naught to v, then we have the time, so time will run from 0 to t, and mass will be starting from m naught and reaches a value of m. It's a very straightforward integral, so we'll have v minus v naught equals to negative gt minus u times natural log of m over m naught, or we can rewrite it as, so we finally get the change in velocity v is equals to negative gt. So this minus will be taken care of, so we have positive u times natural log of the reciprocal, so that will be m naught divided by m. And if we compare it with our previous case where the rocket was moving in free space, it's quite similar except for this extra term negative gt. Now that we have the two equations for the rocket, one moving in free space and the other moving under the force of gravity, we're going to introduce 4 important parameters. So let's start with the first parameter. So we have parameter number 1. Let m0 be the total mass of the rocket. That is, we can say that the total initial mass of the rocket m0 will be given by mf plus mv. Here mf represents the fuel mass, or sometimes also referred to as the propellant mass. mv is going to represent vehicle mass. So that means if we take the help of this particular illustration, let's say we have a rocket and this rocket is going to have some payload. So this payload can be some satellite or could be camera. So the mass of this particular payload is mv. So this is the vehicular mass, and it contains a rocket shell which is filled with the propellant or the rocket fuel, and the mass of this particular fuel is mf. So this is going to be our first parameter. Let's move on to the second parameter. And let us introduce a parameter beta, and this beta is defined as the propellant mass fraction, which is defined as the ratio of the fuel mass divided by the initial mass of the, or the total mass of the rocket, mf over m0. So this is beta. Actually beta is usually of the order of 80%. Typically it's 80%. It's a good value. That means 80% of a rocket contains fuel and the rest 20% is the weight of the payload. So this is going to be defined by the propellant mass fraction beta. Next we have the third parameter. Consider the ratio m0 divided by mv. So that's equals to m0 divided by, so the vehicular mass is the total mass m0 minus the fuel mass. Now if we divide both numerator and the denominator by m0, so we have 1 divided by 1 minus the fuel mass divided by the rocket mass, and we have already defined this as the parameter beta. So we have 1 over 1 minus beta. So this is parameter number 2. Then we define the fourth parameter alpha. It is defined as the mass loss rate. That means the rate of change of mass is equals to minus alpha times the initial mass m0. So if we consider this differential equation as the equation for mass loss, then we have dm equals to negative alpha m0 dt. Then we can integrate both sides. So mass will be, limits of mass will be from m0 to m, and time will be from 0 to t. Solving this gives us m minus m0 equals to negative alpha m0 t, or simply m is equals to m0 times 1 minus alpha times t. So in this particular expression, if we take t equals to 0, then we get m equals to m0. So that means the initial mass m0 will be present in the rocket. And let's say we want to calculate the mass that's left in the rocket after time t has elapsed. Then for that particular value of t, we can determine the value of m, which will be 1 minus alpha t, that fraction times of m0. So let us now try to apply these new parameters into our rocket's equation. So we'll begin with the rocket equation when it's moving in free space. So we have delta V is equals to U times natural log of m naught over m. Now the question is, what happens when the rocket exhausts all its fuel? When it exhausts all its fuel, that simply means that m of f, that means the mass of the fuel, is 0, and in that case m naught will be simply equals to m p. Here m naught represents the mass of the rocket. So that means our equation will have delta V, where delta V is the change in velocity. So the final change in velocity will be equals to U times natural log of m naught divided by m. So here m, of course there's a issue with the symbol. So here m actually represents the mass of the rocket after the fuel has been used up. So that will simply get replaced with mv. So we have U natural log of m naught over mv. Now m naught over mv is the parameter 1 over 1 minus beta. So that should give us U times natural log of 1 over 1 minus beta. Therefore, the final change in velocity for the rocket in free space. And if we consider the rocket which is moving under the influence of gravity, everything will be same except that there will be an extra term. So we have U natural log of 1 over 1 minus beta minus the extra term g, t, and t will be simply tf. So here tf represents the time of flight. Till how much time the rocket was on flight until it finished all of its fuel. Now we can also calculate the value of this time of flight, t of f. We can use this equation, m equals to m naught 1 minus alpha t. So this equation, so m will be, when t is equals to tv, that means all the rocket mass, all the fuel mass has been used up. So we have only the rocket mass, mv, vehicular mass, which is equals to m naught times 1 minus alpha t. You can take mv over m naught equals to 1 minus alpha t. Now we know m naught over mv is 1 over 1 minus beta. So this particular term will get replaced with 1 minus beta. So let's write it down. And when we solve for t, or this is tf, the time of flight. So when we solve for the time of flight, so that will be equals to beta over alpha. So let's just use the expression for time of flight, and then we'll have delta Vf is equals to U natural log of 1 over 1 minus beta minus g times beta over alpha. So this equation means that when we consider the case of a free space movement, it doesn't really matter at what rate the fuel is getting exhausted. Meaning, that means in the absence of gravity, regardless of how much fuel was being exhausted or how fast the rocket moved, the change in velocity, delta Vf, is always going to remain the same. However, in the case of gravity, whenever the gravity is there, it's very important here because the factor alpha, there is always a competition between the parameter alpha and the parameter beta. So we have obtained an expression for the velocity of the rocket when it's moving in free space or under the effect of gravity. Now what we want to do is we want to find out an expression for the distance travel. So for the rocket moving under the influence of gravity, the change in final velocity, delta Vf, is given by U times natural log of m naught over m minus gt. So this change in velocity can be also written as v minus v naught, or vf minus v naught, which is equals to U times, or writing in terms of vf. Now we're going to express v of s as dz over dt Separating the differentials gives us dz is equals to v naught dt minus g times d dt plus u times natural log of m naught. So instead of m, we'll replace it with m naught times 1 minus alpha t times dt. So that m naught and m naught gets cancelled. Then we are going to integrate each terms. So we have integration dz at limits going from 0 to z equals to v naught times integration of dt at time running from 0 to t minus g times t dt, limits going from 0 to t, plus u times 0 to t. We're integrating with respect to time t. We have natural log of 1 over 1 minus alpha t dt. So here what we can do is we can do a little manipulation here. So instead of plus u, we can write it as minus u, and we can take the negative sign inside such that we can apply a property, and that property should give us natural log of 1 minus alpha times t. Fine. So this is simply z, and this will be v naught t minus half g t squared minus u. Now this integration is fairly simple. We can use integration by parts, so we can treat this as the first function multiplied to 1, where 1 will be treated as the second function. We can integrate it by parts. So let me write down the final expression. So this will be plus u times t minus u over alpha times 1 minus alpha t times natural log of 1 minus alpha t. So this is the expression for the distance traveled by the rocket under the influence of gravity. Now, in order to obtain the maximum height, all we have to do is simply replace the time t in the expression with the time of flight. So that's the total time taken to exhaust the fuel, and at that particular time the rocket is going to reach its maximum height, and TF is simply equals to beta over alpha. So that means our expression is z is equals to, replacing the value of TF with beta over alpha, we have minus half g beta over alpha whole squared plus u times beta over alpha minus u over alpha times 1 minus, so alpha times TF will be beta times natural log of 1 minus beta. Or simply we can take beta over alpha as the common factor. That leaves us with v naught minus half g beta over alpha plus u minus u over beta, since we have taken beta over alpha as the common factor, times 1 minus beta times natural log of 1 minus beta. So this is the maximum height attainable, so or z max. And here we can see that's mostly it's comprised of parameters alpha and beta, and if we know the initial velocity v naught and u, then we can essentially calculate the maximum height that is achievable by the rocket.